Alright, good afternoon everyone. Let's get started with EfficientML.ai lecture 4. We are going to start the second part of our lecture about pruning and sparsity. So in the last lecture, let's first go over overview. We talked about the introduction to pruning. What is pruning? Turning a dense neural network into a sparse neural network to save the computation and save the memory, right? And how do we determine the pruning granularity? What pattern do we use to prune the weights, and also determining the pruning criteria? So in the past couple of years, pruning is getting quite popular, from 1989 all the way to optimal brain damage to deep compression. 2016, my paper on iClear and the efficient inference engine. In recent years, the number of publications is surging quite fast in recent years. And also in the industry, like NVIDIA has been using sparsity to accelerate neural network inference, exploiting this 2 to 4 sparsity in A100 GPUs and after. And in this lecture, we are going to cover how do we use hardware to accelerate sparsity. So as a review of what is pruning, so we formulate pruning as this equation to minimize the loss given the pruned weights, such that the pruned weights have less than certain amount of non-zero elements. Okay, so that we turn a dense neural network into a sparse neural network, where WP here calculates the number of non-zeros in the pruned weights, and N is the target number of non-zeros. We also talk about different pruning granularity. On the left-hand side, we have fine-grained pruning, where we have the most amount of degree of freedom. We can prune away any parameters that we want. So as you can imagine, the good thing about this fine-grained pruning is that it's most flexible, but it's most irregular. It's hard to accelerate. On the other side, we have channel pruning, which is very irregular, but you can imagine we can prune less amount of parameters. And how do we select which synapses to prune? The less important parameters will be removed. And how do we select the less important parameters? So a widely used approach is this magnitude-based pruning to select the weights. Who has a large magnitude, we assume they are more important, right? So in this example, we have 4 weights. We calculate the R1 norm, and then we find the absolute value of the R1 norm, and we keep the largest ones and remove the small ones. So that turned out to be a quite effective method, heuristic, to select which weights to prune, just based on the magnitude. Very simple. Not only weight pruning, but also activation pruning. If we remove the activation, it means all the weights associated with that activation is also removed. And here, the entire row of the weights are removed after this neuron is removed. Similarly, for the channel pruning, if a certain channel is removed, all the weights associated with that output channel is also removed. So in the new lecture, we are going to talk about how to determine the pruning ratio. A neural network has many layers, right? Do we prune 20%, 30%, 50%? What is the criteria to determine how much do we prune and how much redundancy are there in each layer? So let's talk about section 1, pruning ratio. How should we find the per layer pruning ratios? So recap, the non-uniform pruning, showing that all the layers, different layers prune different number of parameters, is better than uniform pruning, where all the layers are uniformly pruned at the same sparsity ratio. On the right-hand side is showing the trade-off between latency versus the accuracy, which is the ideal case. So we want a low latency and also high accuracy. Right? So the top left corner is the area that we desire. We want a model that has very low latency and high accuracy. Right? So you can imagine, as we prune the model will become faster and faster and faster, lower and lower the latency, but also it's lower and lower the accuracy. Right? So this black line is uniform pruning, while this red line is using a smarter way to select smartly different pruning ratio for different layers. We can see it can achieve a better trade-off between the latency and also the accuracy. Right. So that's the motivation why we need such non-uniform pruning. Then the question is, how should we find the ratio, the pruning ratio for each layer? So we'll learn this technique called sensitivity analysis. Right? So some layers are super sensitive. If you just prune a little bit, the accuracy will drop very drastically. And in contrast, certain layers are very insensitive. Even if you prune a lot, the accuracy doesn't hurt much. So we want to find those layers are who is super sensitive versus those layers who is very insensitive. And how do we find that? So we can perform this sensitivity analysis given a neural network. So this is accuracy on the y-axis. The x-axis is the pruning ratio, starting from 10%, 20%, all the way to 90%. The more, on the right-hand side is showing that we are pruning more of the parameters. So we pick a layer in the model, and then we find that the higher the pruning rate, right, to the right-hand side from 10%, 20%, all the way to 90%, the more we prune, the more accuracy loss we have. Right? That's as expected, as we saw in the demo in the first lecture. We see that if you prune too much, the accuracy is going to rapidly drop, which is exactly the case. The difference is that here we are just pruning one single layer. Okay, just pruning one single layer. So what we are going to do is to repeat this process for all the layers. Okay, for one layer, another layer, another layer, another layer. Okay, we just repeat this for all the layers. What do we find here? So here we have 6 layers, 6 sensitivity curves. We find some layers are very insensitive to pruning, right? Like the green layer. If you prune a lot, even if you prune a lot, the accuracy barely drops. So that's the layer who is very insensitive. There's also some layers that are very sensitive to pruning, like this blue curve. Even if you prune, for example here, 60%, you're already showing very noticeable degradation of accuracy, versus for other layers, there's barely any accuracy degradation upon 60% pruning. So usually when we are doing experiments, we want to use such sensitivity analysis to do a sanity check, right? Do this sanity check, make sure the code doesn't have any bug, right? So at least in the beginning, the accuracy shouldn't drop. In the end, the accuracy should be very low. If at this point our accuracy is still 100%, there must be something wrong, right? But if here we are barely pruning anything, like 10% or 5%, there might be something wrong as well. Either you are not using the correct granularity or something wrong in the code. That's
it is after the retraining or before the retraining?
This is before the retraining.
Can layers ever be co-sensitive? So they both show high accuracy, but when you remove one, the other one goes down?
Yes, of course. So this sensitivity analysis here is assuming they are independent. Otherwise, the computation will be too much. So that's the trade-off. All right. Question?
What is the type of granularity that you're using here?
Here we are using fine-grained pruning. Fine-grained pruning, right. Okay, so some layers are very sensitive, some layers are not sensitive. So what do we do here? So for the sensitive layer, we probably want to pick a smaller threshold, smaller pruning ratio. And for those sensitive layers, we can prune more. So a very simple heuristic is to find a threshold of accuracy degradation, say 5% or 10%, and then you find the intersection between this threshold versus different sensitivity curve, and find the corresponding pruning ratio. So that's one possible heuristic. You are, of course, welcome to find other heuristics. So this is a very simple, can be automated technique that can be actually automated to deal with different neural nets. Is this optimal? Maybe not, right? We are not considering the interaction between the layers, right? The trade-off is that we don't want to have so many iterations and so many experiments to run. We have limited amount of GPU resources, right? So here we are assuming each layer is independent, such that we can perform the sensitivity analysis for each layer independently. But actually, they are not. That's not the case. Can we go to find better heuristics? And that's what we are going to discuss next. So we want to have the automated approach to perform pruning, right? Rather than manually perform the pruning. Say if you have just a couple of customers who are waiting for a smaller network for you to prune, you can throw like dedicated engineers to each of them. But you have so many customers, so many models to be pruned, like the models for self-driving cars, models for driver monitor system, etc. You need a lot of engineers to do that. That's not a scalable business, right? So to make this thing truly scalable, we really need an automated way, rather than relying on human expert to do the trial and error. So we want to have a push the button solution, right? Rather than requiring machine learning expert, hardware expert to tune different pruning ratio, different layer. We want to have a even non-expert together with this push button solution, this hardware aware, hardware centric auto ML system to automatically find the optimal pruning ratio. So we introduce this auto ML for model compression, right? Automated approach to figure out the pruning ratio, the pruning strategy, given different neural nets. Okay. So on the top is showing the model compression by human. You throw away different perform sensitivity analysis, to try different pruning ratio for different layers. Well, we can actually have an automated approach to use this actor critique model, part of the reinforcement learning algorithm. Try to figure out what is the action. Here is the pruning ratio for each layer. It's like a game. You start with the layer 1 all the way to the last layer. Each step you have a continuous decision from 0% to 100%, which is the percentage you want to prune. And finally, you fine-tune the model to figure out what is the accuracy. If the accuracy is good and the flop is low, then you have a very high reward. Otherwise, if the flop is still high, but the accuracy is already getting much lower, you have a bad reward. Okay? So here, the action is basically giving the compression ratio for each layer, and the embedding is the dimension for this current layer, and this channel dimension, HW, height, width, etc. And the reward is minus error. You want a lower error means you have higher reward, and sometimes we multiply that with log flops, since people realize the relationship between accuracy or error versus the flop is roughly having this logarithmic relationship. So we use the error times log flops to encourage a lower error and also lower flops. And using this approach, we can use the setup for the reinforcement learning problem. The state includes the features like layer indices, which layer it is, number of channels, kernel size, current flops. And the action is the continuous number, which is the pruning ratio between 0 and 1. The agent is the DDPG agent, and the reward would be minus the error if they satisfy the constraint, and if it doesn't satisfy the flop constraint, it's minus infinity. So here we just want to show the result, how amazing it is. Compare with human expert, this is pruning less than 50, the density for different blocks, and the final density given the same accuracy. The human expert can prune 29%, so 91% of the weights become 0. While this AutoML agent can actually prune it to only 20%. And by the way, the human expert is me when I was doing the experiment using 2017. It was quite a while ago to prune ResNet. It took me like a summer, almost quite a few days to complete this, roughly a week or so, to finish this experiment. At that time, we are using only four GPUs in a single server. It was RTX 980. Has anybody ever heard of such old Asian GPU? Okay, we have some folks using that. Okay, now we have 4090, H100, but the old days we have only 4 gigabytes of memory and very Asian stuff. Anyway, it's very time consuming and computation consuming to manually prune different layers. Okay? But you have this automated tool to complete that just in a few hours, just a few GPU hours rather than a week, and have even smaller pruning ratio. And let's see, what does this agent find? What kind of insight does it give us? So I plotted the pruning ratio for different layers, altogether 50 layers. And here is the density for different layers. And we want to compare, here we pruned for 4 stages. Remember, we want to, rather than pruning all the way to the desired sparsity ratio, we want to gradually prune step by step. Each step we prune a little bit. And here we prune 4 steps. So that's why we see the sparsity ratio from high to low to even lower, right? And what pattern do we find here? We find very regular zigzag pattern, right? So there are peaks. There are also crests, and the peaks actually corresponding to those one-by-one convolutions. Those one-by-one convolutions have less redundancy, and they can be pruned less. Okay, that's why they have higher density. These non-zeros, they have higher density. And those low parts, those places corresponding to 3x3 convolutions. Okay, 3x3 convolutions. They have more. The agent thinks it has more redundancy and can be pruned more. Therefore, it has a lower density in this case. So it's quite explainable. The policy given by the AMC agent is quite makes sense. So let's see how does it translate to practical speed up. So this is measured on the Samsung phone, starting with the original MobileNet 1.0. Okay, MobileNet 1.0 has 569 million max. Top point accuracy is 70.6%, and latency is 119 milliseconds. Our recurrent memory is 20 megabytes. And then we perform AMC to cut the flops by half. Okay, starting from 569 million max, now it's only 285 million max. The top point accuracy is actually quite well maintained, from 17.6 to 17.5, and the latencies have a speed up of 1.8 times. So immediately we drop the latency from about 100 milliseconds to about 60 milliseconds. Pretty amazing. And also the memory consumption reduced from 20 megabytes to 14.3 megabytes. We can also specify the target time, the target latency, to be 50%. For example, from 119 milliseconds to 59.7 milliseconds. Imagine it's actually hard, it's difficult to manually design a neural network that has exactly the latency that you want. So that's the beauty of these AutoML techniques, where you can automatically find the best configuration, giving you the target latency, and achieve the best accuracy. So compared with the human design, like shrinking each layer uniformly by 70 to 75%, which gives a inferior accuracy, lower accuracy, and also higher inferior latency. Okay, so that's one technique of using this RL agent to figure out the pruning ratio. Another way to figure out the pruning ratio is called net adapt from my colleague Vivian. So it's a rule-based method to iteratively find the pruning ratio for different layers. The goal is to find the per layer pruning ratio that fits that meet a global latency constraint. And how do we do that? So we start with the original model, and we want to have define a step size. So each step, I want to reduce the latency by a certain amount, and that small amount is called delta R in this case. So given delta R, we want to prune each layer by layer, to see how much do we prune such that we can achieve that delta R latency reduction. Okay, so starting from the first layer, layer A, if you prune a little bit, maybe you just reduce the latency by a very little bit, doesn't satisfy. Then we prune a bit more, until finally we achieve the delta R latency reduction. Okay? And for the second layer, we can prune a little bit such that it can meet delta R latency reduction all the way to the last layer. We prune the last layer, just one single layer, to achieve this delta R latency reduction. And then with short-term fine-tune the model, like 10K iterations, and then measure the latency, the accuracy after the fine-tuning. Some of them may have high accuracy, some of them may have low accuracy. So which layer should we prune? We choose the layer with the highest short-term fine-tuning accuracy to prune, right? Since pruning any of them, they reach the same delta R latency reduction. And of course, I want to choose the layer whose accuracy degradation is the lowest. And we can repeat this process. Each time we prune delta R, another delta R, until we can reach the final target latency. And finally, we can perform this long-term fine-tuning to recover the accuracy for the whole model. And why do we apply short-term fine-tuning in the beginning and long-term fine-tuning right here? Because the first fine-tuning is inside the for loop. We have to repeat it many times to avoid so much computation to only fine-tune it for short term to save the computation. While the final fine-tuning on the right-hand side right here, we perform it only once. So therefore we can afford more computation on that part. So what is amazing about this method is that you can get a chain, a family of models of different latency and accuracy trade-off, right? So here is the latency on the x-axis, here is the accuracy on the y-axis. Ideally, you want a low latency and high accuracy, so the top left corner is the good place, right? So according to this step-by-step, each step you prune the latency by delta R, you get a family of latency accuracy trade-off in the red curve, right? And it's showing that it's better accuracy latency trade-off compared with just applying a multiplier, applying a consistent multiplier like 30%, 70%, etc. All the layers. I think this method is also applicable to pruning large language models these days, where each layer is we can assume each layer is independent, which is not the case, but it's a good approximation. And we just do layer by layer, given a target latency, and also have automatically get a family of models on the trade-off curve. Okay, so that is determining the pruning ratio. And next, we are going to discuss how to fine-tune and how to retrain the pruned network to improve the performance. And then we are going to conclude this part. After this part, we are going to jump into the hardware system part to talk about how to accelerate pruned and sparse neural network using GPU libraries, Torch Sparse library. We're going to introduce that. And also using specialized hardware, including weight sparsity, using efficient inference engine to accelerate pruned weights, and also using point accelerator we designed to accelerate activation sparsity. Okay, so let's switch gear to talk about fine-tuning and retraining to recover the accuracy of a pruned model. As we remember, this is the process. We prune the model, we first train it, and then prune those connections according to the L1 or L2 norm, and then tune the remaining weights. So after fine tuning, we can have a better accuracy compared with without fine tuning. So the accuracy improvement here is all the way like 2.5% from this point to this point, showing that effective fine tuning is very helpful. How should we select the learning rate during fine tuning? And empirically, we find we should reduce the learning rate by like 10x to 100x. That is actually case dependent. Sometimes we want to have the same learning rate, but generally we want to reduce the learning rate since the model pretty much converged at the good local minimum when we are pruning the model. So adjusting the learning rate is something we need to do. And then we want to consider either iterative pruning. So we prune 30% and then fine tune it, and then we prune it at 50% and then fine tune it. And then we prune it at 70% and then fine tune it. This is better than directly prune it by 70% and then fine tune everything. And indeed, this is iterative pruning versus just pruning and retreating only once. That's the difference between this red curve versus the green curve. And that method boosted the pruning ratio from 5x to 9x for LXNet. That's with this iterative pruning versus without iterative pruning. And how do we regularize the weights during fine tuning? So that's pretty similar to when we are training a dense neural network. We want to penalize these non-zero parameters and encourage the model to be small so that we can prune them. So we can either add this L1 regularization or add this L2 regularization. In practice, at least I didn't find quite much difference between these two techniques. Sometimes one of them works better, sometimes the other works better. So on large models, this is a pure empirical stuff. So for example, the magnitude based fine-grained pruning, which basically I did in this paper in 2000, learning both weights and connections, this paper back in 2015, used L2 regularization. Network slimming applied the L1 regularization on channel scaling factors. So in practice, feel free to choose the one and compare which one might be working better. And the rule of thumb is to reduce the amount of parameters that is non-zero. Try to encourage the parameters to be as small as possible, and if it's below a threshold, that will be pruned. Okay, so that concludes the algorithm part, the first part of the neural network pruning. We talk about what is pruning, how to formulate pruning, determining the pruning granularity from fine-grained to coarse-grained, and also determining the pruning criterion, what synapses and ways to prune, and also how much do we prune, how to determine the pruning ratio using rule-based method versus learning-based method, using sensitivity analysis-based methods, and also what are the good practices when fine-tuning the neural network. Let's take a short break before we jump into the next section, which is the system and hardware support for sparsity. All right, welcome back. So let's continue the discussion and jump into the next part, which is how do we accelerate the sparse and prune the network? What is the system and hardware support for sparsity? So we are going to talk about three pieces of work, starting with EIE, the efficient inference engine, to accelerate weight sparsity and activation sparsity. And then we'll talk about NVIDIA sparse tensor core to accelerate 2 to 4 sparsity, which is weight sparsity. And then we'll talk about torch sparse and point accelerator to accelerate the activation sparsity. And starting with EIE, the efficient inference engine. So here the conventional method is we train a model and we directly deploy this dense model for inference, which might be slow and power hungry. So the new approach is to compress the model by pruning it first before we accelerated, it will be fast and power efficient. And remember that the memory access is more expensive compared with computation. So if you can remove a lot of memory traffic, that's very helpful. So the efficient inference engine basically takes advantage of these three aspects: the weight sparsity, where any weight multiplied with zero activation, any zero weight multiplied with any non-zero activation will be zero. So you don't have to store the weight, you don't have to compute on the weight. If we can achieve 90% sparsity, only 10% of the weights is non-zero, we basically have 10x less computation, and we can have 5x less memory footprint. Why 5x here rather than 10x? Because we have to store some metadata, the pointers, the indexes, to indicate where is the non-zero element. Next, we want to take advantage of this activation sparsity. So after ReLU, lots of the activations are zero. So no matter how big the weight is, the multiplication result is zero. So in practice, we find we can achieve about 70% activation sparsity. We also call it dynamic sparsity since it's coming from ReLU and it's dynamic depending on different inputs. And for that, we save about 3x computation since 30% of the activation is non-zero, so about 3x. But no saving for the memory because the memory, no saving for the weight memory because the weight stays the same. And finally, we can do quantization, which we'll talk about in the next lecture. If a number is 2.09, one is 1.92, we can all approximate. We don't need such high precision to represent these weights and activations. We can use low precision to represent them. They can all be quantized to like 2. And in practice, we find 4 bits is enough for the weights by using weight sharing. We're going to talk about in the next lecture. And for that, we can save 4x compared with FP16 and 8x compared with FP32, 32-bit floating point by using 4-bit. Very interestingly, that work was done in ISCA 2016, but modern large language models, 4-bit is also quite enough for modern large language models. We can safely quantize Llama 2, Llama 3, all different models to 4-bit weight using weight-only quantization without losing the accuracy and accelerate them by reducing the memory traffic because the weight is the bottleneck for the memory traffic, no activation for large language models. Okay, so how do we parallelize the computation on sparsity? So on the top is showing that we have a weight matrix, which is 8 by 4, multiplied with this input vector, which is 1 by 4. And this is the output result, and after ReLU, some of them become 0. And this is logically how the weight is stored, and this is physically how the weights are stored. It's using a CSV format. We are storing those non-zero weight, only the non-zero weight, okay? We are not storing the zeros. And here we color them, color the weight using 4 different colors, indicating that we have 4 PEs, PE for processing element, and different processing elements are processing the computation in parallel. So we have 4 different colors, and this is showing the first PE, which is the green PE, right? It's only storing those non-zero elements, W00 corresponding to here, W00, W01, which is here, W42, which is right here, W03, which is here, W43, which is here, okay? And then we are storing the relative index between the previous non-zero and the next non-zero, okay? So this is the, also we have the column pointer showing that where is the starting point? Where is the start of a new column in this matrix, okay? So the first starting point is the first element 0. And then we have the column pointer to be 1, showing that the first entry is a non-zero, column pointer to be 2, showing that Right. The second element, which is W4, 2 is the start of the next column because here we have 0, and then we have the third entry to be the next starting point, and the fourth is not the starting point because this is starting point, this is not the starting point. Therefore, the next pointer is 5. Right. So in this way, we can store a compressed weight matrix by storing only those non-zero entries together with the index and the column pointer. And this is the actual useful weights, and all these indexes and pointers, those are the overhead associated with representing the non-zero elements. So that's why in the slide right here, we are showing the memory footprint is, the saving for the memory footprint is less compared with the computation, since we have to save those extra overhead to store those pointers and relative indexes. So in practice, when we are doing the calculation, when we encounter a 0 in the activation, we ignore that because anything multiplied with 0 is 0. So we skip that until we find another non-zero element. We broadcast it to all the non-zero weight. To the multiplication, here we have 3 multiplications, W01, 21, 71 in different color on different PEs in parallel. And then we encounter the 0, we skip that, and then we encounter another non-zero. We broadcast it to the PEs, to the computation, and then get the activation. And finally, we pass it through the ReLU and get the activation sparsity for the next layer. So here we skipped a lot of zeros in the computation. So this is the microarchitecture for each processing element. Let's go step by step. First, we have an activation queue, which is only storing those non-zero activations. All the zeros are already eliminated to deal with the activation sparsity. And then we use the activation's location to fetch from the pointer, okay, the pointers of the sparse weight matrix, so that we can access the sparse matrix SRAM according to the column start and column end address to get the weight that we want. And then we do the decoding to decode from the 4-bit virtual weight to the 16-bit actual real weight. We're going to talk about that decoding in the next lecture. So now we get a decoded weight. We multiply that with the activation we fetched from activation queue and add it to the previous result. And finally, we have a non-zero detection unit to detect those non-zeros and only store those non-zeros in the activation queue. So what is special here is that we take advantage of the activation sparsity by this leading non-zero detection unit and activation queue, and also take advantage of the weight sparsity by only store those non-zero weights in the SRAM. Since after compression it's feasible to store the weights in SRAM only, we find it that's a great point where after compression it's feasible the weights are small enough so that we can fit them in the SRAM. That's a big change from DRAM to SRAM. A lot faster, a lot less energy consuming compared with having everything in DRAM. And finally, we have this weight decoder where we are having a k-means quantization so that we can store only a 4-bit for the weight. And also for the index, we are storing the relative index to save the number of bits. So we have to do the address accumulation to get the absolute address. But this weight decoding and address accumulation can be done in parallel. And as a result, these FC layers across different models can be accelerated, can be reduced. The flops can be reduced by a lot. From 33x, some of them is 10x because the weight sparsity is different, and some of the LSTMs have less flop reduction because their activation sparsity is dense because it doesn't have radial activation function. So anything that's larger than an order of magnitude is worth exploring. So something theoretically you can only accelerate it by like 10%, then it will take a lot of efforts and may not be worth doing that. But if something you can theoretical reduction is more than 10x, it's very worthwhile to spend efforts on that. So this is the throughput versus the energy efficiency improvement using the EIE, which is showing a quite large improvement, which is actually the first work exploiting the weight sparsity to accelerate neural networks. And I'm very proud it was listed, this paper was listed top 5 most cited papers in the 50 years of ISCA in last year, last fall actually. And here we can look at these 5 papers that is ranking top 5 in the International Conference on Computer Architecture, which is a flagship conference on computer architecture. The first paper is the /2 programs characterization and methodological considerations, which was published in 1995, already 5,000 citations. The second one, we might be familiar with that as the in data center performance analysis of TPU, basically Google's TPU paper, published in 2017. And next one, 1993 and 2016, the EIE, the Efficient Inference Engine on Compressed Deep Neural Networks. So very interestingly, these two are very recent papers, 2017, 2016, right? Only 8 years ago, actually 7 years ago, when was selected last year. 7 years ago, but the machine learning is getting a very trendy and very hot topic in recent years. Despite that, it is only a short period of time, but it's generating a lot of impact in the community. So last year, I was invited to write a retrospective paper for EIE. So what is a retrospective paper? It's usually up after a couple of years. In this case, after 7 years, to think about what is good design, what is the lessons, what is the pros and cons, what's actually applied in industry, what actually didn't get applied in industry. So I get a chance to sit down and think about what is successful and what is unsuccessful. So I summarize them here. The pro is that EIE first demonstrated this special purpose hardware can make it very cost effective to do sparse operations, even if it is like only 50% dense. And EIE can exploit both weight sparsity and also the activation sparsity. Not only save the energy, but also save the cycle, save the latency. And EIE can support this fine-grained sparsity to allow us to allow pruning to achieve a higher pruning ratio. And also this aggressive weight quantization, and actually it's weight-only quantization, like 4-bit quantization to save memory footprint, is still widely used these days. To maintain accuracy, EIE decode the weight to 16-bit before we feed it to the 16-bit arithmetic. But for the memory perspective, it's storing the weight in 4-bit. These days we call it W4A16, 4-bit weight, 16-bit arithmetic, which is a popular term these days. And this approach is reborn in the age of large language models 6 years later. Methods like GPTQ, AWQ, Llama.cpp are all using this approach, weight-only quantization, W4, A16, asymmetric different precisions for the weight and activation. And also the MLC is also using that approach. Some cons. So EIE isn't easily applied to an array of vector processors. The improvement could be using structure sparsity, like 2 to 4 sparsity. And EIE has very high control flow overhead and storage overhead. Like we mentioned, store every line 0 weight, you need a lot of pointers and indexes. And the improved method of improvement could be increasing the granularity of pruning, use coarse grain pruning, so that a larger number of weights is associated with one overhead. And EIE only support FC layers. Actually, that is not necessarily a drawback because these days, large language model and the transformer is getting popular, and they're all FC layers. And yeah, it fits everything on SRAM. Yeah, particularly for TinyML, it's very helpful, but not for large language models. That was actually not exactly true because recently there are startup companies that can fit even large language models in SRAM only. They have multiple chips chained together to do pipeline parallelism to achieve that. So maybe they, so there's a very large design space, an idea that was proposed 7 years ago, very exciting to see they get actually implemented these days by startups, even for large language models. So I should delete not LLM because this year even LLMs can fit SRAM by using many such chips, such big chips. So the first principle of efficient AI computing is to be lazy. That's the lesson I learned from this piece of work. First principle of efficient AI is to be lazy. Try to avoid the work. Okay? There's a lot of redundant computation. We should try to avoid those redundant computation. Quickly reject the work. If it's zero, just don't compute on it. Or use fewer precision, fewer number of bits to represent that, just to be lazy. Okay? Or delay the work. And we find it quite helpful in quite a bit applications for the past few years at MIT. For generative AI, transformer, video understanding, point cloud understanding. Just to give a few examples here, we are going to dive deeper when we are talking about the application-specific optimizations later in this semester. For generative AI, we can exploit spatial sparsity to be lazy, right? When we are editing an image, we are not editing the whole picture, we are just editing a few pixels. So when we are regenerating the model, we can only focus on the pixels that has been edited, the areas that needs to be changed, rather than editing the whole picture. So that is what this work does, SIGE, to take advantage of spatial sparsity. For transformers, there's token sparsity, and we can do progressive quantization. For example, when people are talking about natural language, there's a lot of redundancy. We can safely remove a lot of the tokens. Not all tokens need to attend to all tokens. We can use sparse attention, Spartan piece of work, sparse attention to accelerate transformers. For videos, there's a lot of temporal redundancy. We don't have to do the 3D convolution, both in the spatial dimension and also in the temporal dimension. Rather than that, we can use a very simple shift operation to model the temporal relationship because different adjacent frames are very similar to each other. And point cloud is naturally sparse. It's widely used in autonomous driving, self-driving cars from LiDAR sensors. Lots of the spaces is actually zero. So we can take advantage of that using torch sparse, like ACC, etc. So in the future, we envision these future AI models will be very sparse at various granularities for the weights, for the activations, fine-grained, coarse-grained, structured, unstructured, and co-designed with the efficient system, either GPU accelerator or specialized accelerator. The sparse models will be very efficient and accessible. So feel free to, we have open-ended project later this semester, so feel free to explore more about sparsity. Okay, so that's the first part, which is efficient inference engine, accelerating both weight sparsity and also the activation sparsity. Now let's switch gear to talk about NVIDIA Sparse Tensor Core to accelerate models with M2N weight sparsity. So we have seen this picture in the last lecture. On the left-hand side is the logical representation of a 2-to-4 sparse weight matrix. It's 8 by 8, but for every 4 elements, four entries, 2 of them must be 0. And the second 4 elements, 2 of them, first one, the last one, they're 0. Okay? So when we are representing them, we can actually condense these 8 elements into only 4 non-zero elements. And is that enough? Actually not. We still need the the index matrix to represent which location does this non-zero entry belong to. Okay, it can possibly coming from 4 different entries, since every 4 elements, 2 of them is non-zero. So each non-zero can come from location 0, 1, 2, 3, right? So how many bits do we need for each location? We need 2, we need 2 bits because we have 4 possible locations. Okay? We have 4 possible locations. So we need 2 bits for each non-zero element. That's why here it's narrower. And 4 elements, each element is 2 bits, so altogether 4 bits, that's exactly 1 byte to store the metadata. It's quite efficient. And how do we do the computation? On the left-hand side is showing the dense version. Okay, we have a dense matrix. We have a dense matrix to do the multiplication together. Everything must be multiplied with everything. Okay. So on the right-hand side is doing the sparse matrix multiplication. This is the 2 to 4 sparsity. This is the payload. This is the index. Okay. So for every non-zero element, we need to know which entry on the B matrix it needs to be multiplied with, right? So here we use this index matrix to select from the red B matrix to select the corresponding non-zeros using this mux, okay? And to only multiply the dot product, multiply only with the corresponding non-zero elements, such that the weight and activation, the location will be matched. And then we do the accumulation and put back the result in the write it into the output activation memory. So that's how it's actually a very smart idea to deal with the 2 to 4 weight sparsity. So just using this index as the selector to the max, and then select those non-zero activations. Select those activations corresponding to those non-zero weights. And let's see the latency, the speed and also the accuracy trade-off. So here is showing the speed, and here is showing the accuracy. The speed right here, the speed up, the top here is 2x, so that's the theoretical speed up, because every 4 elements, 2 of them is non-zero. So theoretically, 2x speed up. Actually, the measured speed up is about 1.9x when the matrix is pretty big. When the matrix is pretty small, the speed up is also small, like 1.2, 1.3x. The accuracy is actually quite well maintained from dense P16 to sparse P16 all the way to sparse int8. The accuracy is very well maintained. It's also showing that sparsity and quantization, they can be well combined together if you compare the dense unquantized version versus the sparse quantized version. 33.7, 33.7, pretty much well maintained across the ResNet, wide ResNet, HGG, etc. Different models. Which is showing the 2 to 4 sparsity has quite good speed up and also quite satisfying accuracy. Okay, lastly, let's talk about the activation sparsity. Okay, we walked through weight sparsity, and now let's talk about activation sparsity, including using torch sparse, done by the TA Haotian and also Shang, to accelerate the sparse convolution, and also using point ACC to build a specialized hardware accelerator for sparse convolution. So let's first talk about what is sparse convolution on sparse input. So the left-hand side is showing the conventional convolution. Okay, so the output is still dense, and all the weights need to interact with each non-zero input. Okay, so the drawback is that the sparsity pattern will dilute. Initially, it is very sparse, but after a while, the feature map will propagate. That the non-zero element will propagate, and after a few layers, it will become very dense. So what sparse convolution does is that the activation sparsity pattern preserves the pattern between the input and output. So this is the weight in blue. This is the input activation. The yellow is the output activation. The output activation and the input activation has exactly the same sparsity pattern. By sparsity pattern, I mean the non-zero element location is exactly the same between the input and the output. The difference is that the sparsity pattern will dilate versus the sparsity pattern will be the same. Okay, so what is the implication on the computing side? So the conventional convolution, every weight entry will interact with the input. But for the sparse convolution, it's not the case. If the output doesn't have any, it have a zero entry in the output, the corresponding weight will not interact with the corresponding input. So we can walk through a few more examples. The fourth location doesn't interact with this weight because the output is zero. So this input will not interact with this input. Versus on this case, this input need to interact with this weight to produce this output. So until right here, we have a one interaction. So to produce this output, which is non-zero, this weight needs to interact with this input. Again, no compute. Finally, one more compute. Because in order to produce this output, the weight here needs to interact with the activation here. So for this part, the dense convolution require 9 matrix multiplications, 3x3 kernel, but the sparse convolution only require two matrix multiplications. Why matrix multiplication? Because the kernel has the channel dimension which is not shown in this figure. So the key part is that we need to build a map. The map is the relationship between the input activation, the output activation, and the weight. So for example, here we are building this map between the input activation, output activation, and also the weight. And we sort them by the weight, showing that this is weight stationary. For example, we pick weight W minus 1, W minus 1, minus 1, okay? And only a subsection of the weight, of the input activation need to interact with the output activation. For example, here P0 only interact with output 1, and P3, P1, 0, 1, 2, 3, P3 only interact with output 4, 0, 1, 2, 3, 4. As a result, only a subset of the input dots need to interact with the weight, W minus 1, and only produce two outputs. And similarly, we go through all the weights, W minus 1, 0, W 0, 0, it has more interactions, W 1, 0, W 1, 1, and we get the entire mapping between the input, weight, and output. And as a result, we find the computation workload for different weight, W minus 1, minus 1, minus 1, 0, the workload is different. Okay, so this is 2 workload, 1, 1, 2, here is 5, right? Which is causing the imbalance between different matrix multiplications. So what we do here, we do adaptive grouping. So we group the matrix multiplications of similar size together so that we can do them in a batch, using the batch matrix multiplication, okay, which has more parallelism to fully exhaust the GPU parallelism. But you can imagine we have some overhead, padding overhead. Okay, we are wasting some of the computation because like W minus 1, 0 doesn't need to have the second computation, but we have to pad it. So that's the trade-off between the computational overhead and also the regularity. Ideally, we want both. We want it to be low computational overhead and also high regularity, but that's not the case. The first example is showing we are having an overhead, but the regularity is the worst. right? GPU have to work lockstep. So different threads here, they are out of sync. That's not good. One extreme case, we can patch it to the max computation workload. And as you can imagine, it has a lot of redundancy. So here, lots of overhead is the worst, and the regularity is the best. So what we choose is to balance the overhead and regularity by using this dynamic grouping, computation grouping. Okay, so this is the first group. This is the second group. These computation have similar batch size, and this is the last group, and which have a pretty okay overhead and okay regularity. So that's the qualitative analysis. So here's the quantitative analysis. So we are increasing the number of groups from 0 to 26, and we find that there's a sweet spot right here, roughly 6 groups give the best speed up over the baseline. First, increase and then decrease. So this is how we group them together as a visualization, and that's why it's very crucial to do algorithm and hardware co-design, because for different benchmark, static TD versus new scenes, the sparsity pattern is different, therefore the grouping strategy is also different. And here we are comparing the baseline versus fixed grouping versus adaptive grouping. For different benchmarks using adaptive grouping, actually, this is quite advantageous compared with the fixed grouping. And for new scenes, sometimes the adaptive grouping is worse because fixed grouping has the best T flops per second, but adaptive grouping is faster. So here is showing the T flops per second, which is the throughput measured on the GPU. But not all of the computation is useful. Some of them is actually redundant. So some of them doesn't count toward the useful computation. So the actual speed up, the winner of the speed up is still the adaptive grouping. Because here we are doing a lot of redundant work. So the T flops is high, but the end-to-end throughput speed up is not high. Okay, so following torch sparse, we continue work on torch sparse plus to overlap the memory and computing. So this is dealing with, again, it's dealing with the LiDAR sensors in autonomous driving applications for like 3D segmentation, 3D detection, 3D scene reconstruction. So we have a sparse kernel generator and a sparse auto tuner to auto tune the design space. And this is comparing the speed up across NVIDIA's engine to simple engine. The speed up is quite significant. And I want to highlight one smart design right here to overlap the memory and computation by reordering. So what is reordering? So here is the mapping between the weight on the top in black. Here we have 9 different weights, 3x3 kernel. And then we have different outputs from B0, B1, B2, B3, all the way to B7. Okay, in order to produce right here B0, we have to multiply A00 with A0, W00 with A0, W01 with A2. So that's the mapping between the output weight, between the output, the weight, and also the input activation, right? So adjacent two groups. Okay, adjacent two activations, they are grouped together. They are calculated in parallel. We have 2 in this example, and in practice, could be more. So we are going to find the common, actually all the red elements here is redundant because ideally it didn't need to compute, but since its neighbor has that entry, the first one also needs to compute on that. So altogether there are 12 redundant computation right here. A smarter way is to actually merge them by treating each element here as one digit in the binary representation, and we can simply do the reordering by sorting them. For example, here after sorting, B6 and B0 are getting together because they are very similar in the sparsity pattern. And B7 and B5, they get sorted together because their pattern is similar. B4 and B3, they are together because their pattern is very similar. And here, the redundant computation reduced to only 10. We can also apply column splitting to perform even fine-grained sorting. For example, we can split the channel by 3 such that the groups now have a better similarity and have less redundancy. Okay. But now after that, the redundant computation reduced from 10 to 8. So we can use this approach to reduce the redundancy, and of course we are increasing a little bit of overhead by reordering, by sorting, and also by column splitting, which the gain over will overkill such overhead. And finally, I will introduce a part of accelerator to accelerate the sparse convolution. Since we'll have to find the mapping between the input activation, input point cloud, the output point cloud, and also the weight, right? What is a smarter way if you have a specialized accelerator to find such mapping? So given one example of W minus 1, we first overlap the input and output point cloud together, and W minus 1 correspond, we shifted in the reverse direction from the center. This is top left corner. We shifted bottom right, okay? And shifted means we just add the index, okay? Add the index by 1, since we are shifting the reverse direction of minus 1. We shifted, and then we do a merge sort with the output point cloud's index. Okay, so we do a merge sort for these two arrays. Merge sort means we sort them according to we sort them, and then we find the intersection between these two arrays. These two are identical. These two are identical, so that we can put Q1 and P0, Q4 and P3 right here in the mapping. Associate that with W minus 1. So this part can be accelerated by hardware. Okay, this intersection unit between two arrays. We can very efficiently find the intersection of two arrays. Similarly for W11, we shifted in the top left corner, and then we do the merge sort again. At first, adding the minus 1 corresponding to W11 to the index for each non-zero element. Here we have 5 non-zero elements right here corresponding to here, and then we find the intersection between them. 1, 1, 1, 1, they are the same, and here 3, 2, 3, 2, they are the same. Therefore, we put them together in the mapping array for P1 and Q0 from P1 and Q0, P4 and Q3, and associate them with W11. So this is the speed up over the GPU and CPU, actually a pretty big speed up and energy saving using accelerator versus using CPU and GPU. With that, let me summarize today's lecture. We first talk about the algorithm part, then we talk about system and hardware part. In the algorithm part, we talk about automatic ways to figure out the pruning ratio using sensitivity analysis, very practical way, using the reinforcement learning-based method, AMC, using net adapt method. And also we talk about how to fine-tune and recover the accuracy of a pruned model. And lastly, we talk about system and hardware support for different granularities using EIE, efficient inference engine, to the full sparsity, sparse tensor core, and torch sparse and point ACC. In the next lecture, we'll jump into a new chapter about quantization. So we'll talk about FP16, FP8, FP4, int4, int8, the basic concept of neural network quantization, and also common quantization methods. Lab 1 is released today, so you are welcome to check it out. Pay attention to the submission date. That's all for today's lecture. Thank you.